Okay, go ahead.
Okay, so welcome everyone, and welcome Vika. This is the second part of Victoria Gitman's talk about AC, DC, and fragments of second-order arithmetic.
Okay, thanks, Roman. So in the first part, I did a lot of the groundwork to show you a high-level proof of this result, which is that you can have a model of second-order arithmetic, a full second-order arithmetic with the choice scheme in which the dependent choice scheme fails for a pi1-2 assertion. And so, as I said, I will give a high-level overview of the proof because the details are extremely technical and nasty. But I think the high-level overview already gives an idea of what is happening, or should give a good idea of what is happening. And let me recall the strategy. So what we are going to do is we will come up with a clever forcing extension, and in it find a symmetric submodel in which countable choice holds, but DC dependent choice fails for pi1-2 definable relation on the reals. I wonder what that is. So I didn't kill sound on everything. And then we will take the full standard model of N, and that is going to be the witnessing model here. Okay, so the key is going to be the pi1-2 definable part, and I'll give some initial models that didn't work to begin with. But first, I want to quickly go over two things that we talked about last time, just to have it fresh in our minds. So let's look again at the Pfefferman-Levy symmetric model, sort of classical symmetric model that we constructed. So remember, in order to construct a symmetric model, first you need a forcing, and then you construct the forcing extension. And then you find the clever group of automorphisms of this forcing, and then you find the clever normal filter on the subgroups of this group. So in the case of the Pfefferman-Levy model, we forced with an omega length product of forcings, and then the subgroups, the automorphisms were the ones that stayed inside each element of the product, and then the subgroups fixed some chunk of the product. And this will be a pattern that we will see later in a moment also, that the way that you usually pick the subgroups is they're the ones that fix some chunk of the product. Okay, so and the key property of the symmetric model was we didn't know which sets ended up in the symmetric model N, but we didn't know exactly which sets of ordinals ended up in it, and these were the ones that arose in some initial segment of our forcing. So in some finite chunk of our forcing, we will see the same pattern in the models that I will show you in a moment. So I want to review one more thing. So I'm going all the way back to the useful forcing notions. And the first models are going to use the notions at omega kappa and at omega 1 kappa. Okay, so at omega kappa, for instance, was the forcing that added kappa many new reals, kappa many new subsets of omega. And there's nothing special here about kappa. Kappa is just an indexing set. You could have, instead of kappa, used any set of size kappa and indexed by that, and you would get an isomorphic forcing notion with the same forcing extension. We just like to index things by ordinals because it's easy. Okay, so here the conditions were finite functions. We also had this example at omega 1 kappa. Again, instead of kappa, you could use any set as an indexing set. And in the case of omega 1, where you're adding subsets to omega 1, we use countable conditions. Okay, so in fact, in a model that in the construction that I'm about to show you. So now let's go to the new stuff. So in the construction that I'm about to show you, we will actually force with add omega 1. So we'll be adding omega 1 many subsets to omega 1, but we won't use omega 1 as the indexing set. We will use a set of size omega 1. So the forcing is going to be essentially the same. It's isomorphic, same for forcing extensions and everything. But using a different indexing set is going to help us to pick out the automorphisms that we're interested in. So in fact, the indexing set that we're going to use, and I should say, what I'm constructing is a classical symmetric model in which countable choice holds, but DC fails, and it's a very old construction due to Jensen. And as I said, we will look at a few examples first, see why they don't work for the purposes of our theorem, and then and then I'll tell you how we fixed the issues in the construction that we came up with. So here's this classical model. The forcing is at omega 1, but instead of using omega 1 as the indexing set, we use the tree omega 1 to the less than omega. So this is a tree that at every node branches omega 1 many times, and I have a picture of the tree. And the reason is it will help us define the kind of automorphisms that we want. Conditions are exactly the same. We take countable subsets of the matrix that we're going to fill up. The forcing, the order is again extension. And one of the key properties of posets at omega 1 anything is that they're countably closed. So countably closed means that any descending omega sequence of elements in the partial order has a lower bound. And this will be key to showing a certain property of this model. Okay, so let's fix a generic and start talking about the kind of automorphisms that we want to have. Okay, so we have this tree. The tree omega 1 to the less than omega obviously has lots and lots of automorphisms. You can switch nodes, right? These are sort of the obvious automorphisms and many others. Okay, so the automorphisms of the partial order are going to be the ones generated by the automorphisms of the tree. So the automorphisms are going to come from the automorphisms of the indexing set, which in this case is this tree. Okay, so we know what our automorphisms are. Now I have to tell you what are going to be the subgroups that we pick. And in order to do that, I need to define this notion. Let's say that a countable subtree of this tree, now let's call it good. I call everything good. I'm not imaginative. Okay, so let's call it good if it doesn't have an infinite branch. So good trees are countable ones without a branch. And then, so with each such good tree T, let's associate the subgroup of all automorphisms which fix this tree. And then the subgroups that we will use to generate the normal filter are going to be the ones which all of our automorphisms are generated by the tree one. So they're going to be ones that fix conditions on the nodes in a good tree T. So the intuition here, before you look at anything else, is we want to have this symmetric submodel with a relation that does not have an infinite branch. And somehow we will use the fact that the parts of the forcing that the subgroups fix come from trees which don't have a branch. Okay, so now we have the automorphisms, we have the subgroups. Recall that we say that a name is symmetric if it's fixed by everything in one of our special subgroups. So a name being symmetric is actually witnessed by one of these good trees T, because everything which fixes this tree fixes the name, and then the name is hereditarily symmetric if it's symmetric, and then every name which occurs inside it is also symmetric. Okay, so in the Pfefferman-Levy construction, we fixed initial finite segments of our forcing. Here we fix a part of the indexing tree, which happens to be a countable subtree without a branch. It's a much more complicated object, but the idea is exactly the same. You fix some part of your forcing, and we have an analogous theorem. We don't know which sets end up in N, in the symmetric submodel, but we do know exactly which subsets of ordinals end up in it. And they're exactly ones which arise in the part of the forcing associated to some good tree T. Okay. So what does this forcing actually add? Let's go back to this slide for a second. Well, one of the things that it adds is it adds a tree isomorphic to omega 1 to the less than omega, each of whose nodes is a new subset of omega 1. And this is the object that I'm very much interested in, is this very bushy tree of new subsets of omega 1. Now, this tree has a name, has a p name in V. In particular, it has a very canonical p name, in the same way the generic filter has a canonical p name G dot. And when you analyze this canonical name scripty tau dot, it's very easy to see that it's hereditarily symmetric. It's symmetric because of our choice of automorphism. Every automorphism fixes it. And then it's not difficult to see that all the names in it are also symmetric as well. So in particular, this tree is going to end up in the symmetric model. But here's where something really interesting happens. So the full forcing extension sees this tree is isomorphic to omega 1 to the less than omega. The symmetric model N will not see this. In fact, the symmetric model N is going to think that this tree doesn't have a single infinite branch, which is extremely weird because it obviously does. So let me sketch an argument of this. It just gives you, again, it gives you a high level idea of why this is true. And the details, it's just a standard use of automorphisms in these kinds of constructions. So what you do is suppose that in the symmetric model N has, there is some infinite branch B through this tree script T. Through this full tree. Well, okay, if it's in N, then it has some hereditarily symmetric name, sigma. In particular, it is symmetric, and therefore this is witnessed by some good tree T. Because to be symmetric means that you're fixed by everything which fixes T. Okay, so we pick such a witness T. And because we chose as witnesses trees that don't have a branch, the branch B in particular has to lie outside of T. At some point after finitely many steps, it lies outside of T. And then you use an automorphism argument to derive a contradiction, that this cannot be the case. So this is the idea for the argument why DC fails in this model. Okay. Let me also try to give an idea of why countable choice holds in this model to see the issues that we will have to face later. Okay, so how do you show that countable choice holds? Given a countable family of non-empty sets in this model, and we want to build a choice function that is also in this model. Now, in order to build a choice function, I have to argue that there's a choice function with a hereditarily symmetric name, in particular with a symmetric name. So let's see how we will do this. So let's fix a family let's fix a family F of sets of non-empty sets Fn in the symmetric model, and in particular, since F is in the symmetric model, it has a hereditarily symmetric name sigma, and this is witnessed by some good tree S. And now we will use the countable closure of the partial order to build the choice function. Okay. So we start with some condition P0 below P, which we know that it happens to be true that the zeroth element of the family has something in it. So there is a condition P0, which forces that some name tau 0 is in sigma 0, and tau 0 is a hereditarily symmetric name. And let's pick a witness. This is going to be the tree T0. And I can keep doing this, obviously, for omega many steps. So P P1 is going to be a stronger condition, and it's going to decide that some tau 1 is in sigma 1, and P2 is going to decide that tau 2 is in sigma 2. And the natural, each of these are hereditarily symmetric names. I can find by countable closure a condition P below all of them. So in particular, P is going to agree that tau I is an element of sigma I. And whenever I have such a sequence of names, I have a canonical name tau for the sequence. And now I would like this name tau to also be symmetric. But the problem is this: the natural witness to tau being symmetric is the union of the trees that witness that each of the names were symmetric. But the trouble is, so a union of countable trees is a countable tree. But the problem is that as I was unioning up the trees, I may have grown an infinite branch, and therefore T, this union, won't work as a witness. And therefore, when I choose the witnessing trees, I have to choose them very carefully. And the way that we will choose them is we will make sure that they widen out. So the trees are widening out, but aren't growing on top of each other. And what this means that their only intersection is going to be what it needs to be, which was this original tree S. And again, you can do that using automorphisms. This is not a big issue. Okay, and this is the sketch of the argument. And this is a very nice model. Countable choice holds, DC fails. But the problem is that the witnessing relation, this tree script T, is not a tree of reals. It's a tree of subsets of omega 1. So our model of second order arithmetic sees none of it. And you can do, so Simpson suggested that we somehow rework this construction and do a further collapsing forcing to make all of these subsets countable. We tried and utterly failed. So there's an obvious obstacle, and there didn't seem to be any clear way of resolving it. And so the obvious next thing to do is to ask, okay, why did we have to have add subsets of omega 1? Why couldn't we add subsets of omega? And reason is that we made a crucial use of countable closure, which at omega kappa does not have. So the question was, could you somehow make it work with add omega 1 to the less than omega? And what we figured out was that the answer was yes, you could make it work. And the way that you make it work, so first of all, the partial order is exactly the same, only on the nodes of the tree, we are now adding reals instead of subsets of omega 1. Conditions are now finite instead of countable. This forcing obviously isn't countably closed, which we seem to have crucially used to show that countable choice holds, but it has another very nice, very useful property, and that is it has the countable chain condition CCC, and that means that every anti-chain of this partial order is countable. And the way that it usually works is if you can make a construction work using countable closure, there is another way to make it work using CCC, and it turned out to be true here. So there is another much more complicated argument which uses CCC instead of countable closure to show that in the symmetric model, countable choice holds. Okay, so now we're in a much better place because we have a relation on the reals. So our model of second order arithmetic could potentially see it if this relation was in some manner definable. But this is the problem. It's completely so we need two things about the relation to be definable. Its domain and the actual relation, the ordering. And it's not clear why either one would be definable. So what is this tree? The domain of this tree is some collection of the new subsets of omega, which we added, the ones that are exactly the ones added by the generic filters add omega 1. But the problem is, if you force with add omega 1, other than adding the actual real on the generic filter, it adds continue many more generic reals. So other than the reals, which are nodes of this tree, there are continue many more generic reals floating around. And we have no way of distinguishing the ones that are on the tree. It just seems hopeless to somehow pick them out. So it's completely unclear that the domain here would be definable. And the ordering seems to be even worse, because there's absolutely no connection between the reals that you added and where they are on the tree. So this also seemed quite hopeless. You seem to need a different forcing, and it turned out that you need a much more complicated forcing. So let me try to explain to you what this much more complicated forcing was. So first, I will tell you the ingredients that we needed to build this forcing. So before I do that, let me just stop for 1 second and ask if there are any questions.
Well, Vika, I was going to ask, why not just add continuum many, reals? Maybe that'll solve some problems, but it sounds like everything would get even worse, maybe.
I think it gets even worse.
Yeah.
Because you still cannot distinguish out the reals that you added out of all the ones that you kind of added accidentally, meaning that they weren't on the actual generic filters.
Okay, and I was also going to ask what's the difference between tau and sigma, but that's the automorphism.
On which slide, Aaron?
When you were giving kind of the proof, when you're going back to
here.
Yeah, I was like, what's sigma and tau? The difference between those two?
Okay, so sigma is the name for the family of sets, and then tau is the name of the choice function that I'm trying to build.
Mm.
Okay, so I have sigma, and I'm showing how I build the name for the choice function, and then the name has the desired properties to end up in the symmetric model.
Okay.
Okay.
Sounds like maybe you're related to your obstacle or something. I'm just kind of seeing it on.
No, it's just the two. It's just showing. So one is. So what does it mean to verify that countable choice holds? It means that you have a family. That you have a countable family of non-empty sets, and you need to build a choice function, right?
Okay.
So since I'm working with the forcing extension, everything is about names. So if I have a family, I take a name for it, and then I use the name for the family to build a name for the choice function. And this is going to work exactly the same with the CCC, only in a much more complicated way. The way that you build it, the argument is sort of uglier. Okay, so let me have a sip of tea. All right, so what is the forcing that we ended up using? So these are the ingredients first in building. So first, what we would like to have is we would like to have a sequence Pn, an omega length sequence Pn of forcing iterations. So remember, a forcing iteration does several steps of forcing, several consecutive steps of forcing all at once. So Pn is going to be an iteration of length n, meaning that it does n steps of forcing at once. Okay, so I have this sequence of iterations, and I'm not doing an omega length iteration here. I just have a sequence of iterations, and they happen to have be coherent in the sense that longer iterations just extend shorter ones, and each of these iterations is going to add generically an m length sequence of reals, and in fact it's going to be the generic is going to be determined by this m length sequence of reals. So if you think back to sex forcing, I showed you sex forcing, which is this forcing with perfect trees. There the generic was determined by a single real. And if you do n steps of sex forcing, the generic is going to be determined by an n length sequence of reals. So you can basically even though the generic is a collection of perfect trees, you can think of it as really being an n-length sequence of reals. Okay, so I have this omega length sequence of iterations, and they're extending each other. Each one adds an n-length sequence of reals. And I want the property, this isn't difficult. So given these PNs in a forcing extension, I want the collection of all the generic sequences of reals that it adds to be pi1 to definable. In fact, at omega 1 has this property also. So this isn't very special, but it will be very useful. Okay, and now the forcing is going to be this. So I will use these iterations to build my forcing. We will use trees again as an indexing set. So elements of my forcing are going to be functions from a finite subtree of omega 1 to the less than omega, not a finite subset. I really want a finite subtree now. And then the nth, and then a node on the nth level of the tree is going to be mapped into an n-length, into the n-length iteration. So a node here on the first level of the tree is going to come from P1. A node on the second level is going to come from P2. And since my iterations are extending each other, the conditions on the higher levels are going to extend conditions on the lower levels. So if I have, let's say, a generic for this partial order, and on each of its nodes, it adds some n-length sequence of reals, the ones on the higher nodes, the sequences on the higher nodes are just going to extend the sequences on the lower nodes, which means I know exactly what the ordering of the sequences is. It's just extension. So I will have the ordering on the tree that I add. The generic tree is going to be completely free. And if you are a set theorist, you will recognize that this is a nonlinear iteration along this tree. And nonlinear, usually we iterate along ordinals. Nonlinear iterations get much messier. Okay, so we have solved the problem of the order with this trick of using n-length iterations. The sequences that I add on the higher levels are just extensions of sequences that I add on the lower levels. But we need uniqueness. We need to make sure that we haven't added sequences on the side, that every sequence that we have added is a node, every generic sequence. We can recognize the generic sequences. This collection is pi1 to definable. We just need to make sure that, unlike in the case of add omega 1, we haven't added any generic sequences that don't lie on the tree. So we want every generic sequence that we added to appear somewhere on this tree. It's a uniqueness property that common forcing doesn't have. And it's not difficult to see that the forcing has the CCC, so we will be able to verify countable choice exactly as we did before. Okay, so once we happen to find iterations with this uniqueness property, we will be done because the strategy is going to work. We will have the domain of the tree is pi1 to definable because of this. And the ordering is just extension, which is pretty trivially definable. So we just need Pn with the desired properties. And Pn is going to come, it's not going to be sex forcing, but it's going to be a sub-forcing, a very cleverly constructed sub-forcing of sex forcing with extremely nice properties. So elements of the partial order. So this is Jensen's forcing J. I will call it J in honor of Jensen. And it's going to be constructed in L using the guessing principle diamond. So it's a sub-forcing of sex forcing. So its elements are going to be perfect trees, but we won't take all perfect trees. We will pare down the trees that we take. And so this forcing is going to have two very useful properties. One, unlike add omega 1, which adds continuum many generic reals, this one is going to add a single unique generic real. So it has a unique, it has some kind of a uniqueness property that you can work. And it will have the CCC, which is going to help us verify that our ugly tree forcing has the CCC as well. Okay, the construction of Jensen's forcing is already pretty involved. So what I will tell you is this. If you're familiar with the construction of a Suslin tree using diamond, it's a similar idea. You construct it in omega 1 many steps using diamond to guess anti-chains along the way. And then when you guess one, you seal it. And that's how you essentially construct Jensen's force. Now, at that time, when we were working on this, there was a very recent theorem of Kanave and Lubetsky, which extended the uniqueness of generic reals property of J to omega length products of J. What does that mean? So what they showed that if you have a generic filter G for a finite support omega length product of J, then the only generic reals that you add are exactly the ones added by each of these omega many J's. You don't add anything else. And the argument here was the motivating factor for us. So we got our own version of uniqueness. So our PNs were in fact JNs. So these were n-length iterations of Jensen's forcing. And what that does is the generic is determined by an n-length sequence of reals. And let's call T this tree iteration using these JNs. And what the forcing obviously adds is it adds a tree isomorphic to omega 1 to the less than omega, where the nodes on level n are these n generic sequences for Jn. And this is what we showed. This was the key, which makes everything work. So if G is a generic filter for this tree iteration boldface T, for this partial order that I showed you, then the only algebraic sequences of reals for Jn are those that physically appear on the nodes of the tree. And therefore, the domain of the tree is pi1 to definable, and then the order is completely trivial, and we are done. Okay, so this completes the proof of the main theorem, or at least the high-level outline of the proof. Now, so I want to show you something which is cute. And Corey asked me a question last time, which I didn't understand, but I asked him afterwards and I understood it and I couldn't answer it. But it got me thinking about the fact that the following is obviously true using Schoenfeld's absolutes. Okay, so we went to this forcing extension and then down to the symmetric submodel to construct this large model a full second order arithmetic with the choice scheme, in which pi1 to DC fails, and it's obviously a beta model. But in fact, using Schoenfeld's absoluteness, you can now show that such models must exist in any model of ZFC. And I think that this is true. And I asked Corey, and he agreed with me also. So hopefully it is true. It seems like a simple argument. This is what I want to do. Okay, so start in any model V. It has its constructible universe L, which has this partial order T, which I forced with. So let's take a generic, let's take a V generic filter for this partial order. In particular, LG is contained in VG, and inside LG sits this model N. which has the beta model script M. Okay, but M has using sort of the usual Löwenheim-Skolem argument, a countable beta submodel with the same properties. The key here is that it's countable. To make it a beta submodel, when you're closing under witnesses, whenever you have a relation and it's ill-founded, include the witness for the ill-foundedness of the relation. Okay, this also seems to be straightforward. But because the model is countable, it's now coded by a real. And it's a sigma 1-2 statement to say that such a model exists, and therefore by Schoenfeld absoluteness, I have to have such a model already inside B. And I can't believe that I never thought of it before. It seems easy enough. Okay, because I have 20 minutes left, I do want to talk about one more thing, and this is going to be very set theoretic in nature, but this is something that I think is extremely interesting, and it's the consequences of this theorem for structures of certain set theory. But before I do this, again, I need a sip of tea, so I will ask if anybody has questions.
I have a quick, just clarification question about the last slide.
Oh dear, is it wrong?
No, I think it's correct. I think I'm just not understanding something. So you do this forcing, and so you're not taking a symmetric submodel. Am I understanding correct?
I am. No, the script M here comes from the symmetric model of L of G that I showed you before.
Okay, I see. But it's in the thing because you have more sets, and being a beta model of this is absolute then.
Exactly.
Okay.
Everything here is absolute because everything is transitive, right?
Okay.
Not with any weird models.
Okay, that clears up my misunderstanding then. Thank you.
That's right. It's weird. It's so simple, and we just never thought about it. Anyone else?
Why do you need an L and a V?
Because this forcing that I do only works in L. Jensen's forcing, it's completely unclear how to define Jensen's forcing outside of L.
Okay.
So it doesn't just need diamond. It needs L with witnesses. It needs condensation. It really seems to. So me and Corey actually at some point thought about generalizing Jensen's forcing outside of L, and it seemed completely unclear how to do it. Mm-hmm. So this is the reason that I always need L. Okay, so let's talk about set theory. I'm a set theorist, so I like this part much more. So I said at the beginning that models of second order arithmetic were really in a hidden way models of set theory, and now I will tell you precisely what that theory is. Okay. So let me define what Z of C minus is. Z of C minus is, roughly speaking, set theory without the power set axiom. But once you remove the power set axiom, things start to become extremely weird, so you need to be very careful. So not only do I want to remove the power set axiom, I want the collection scheme instead of the replacement scheme, and I want the well-ordering principle instead of the axiom of choice. So axiom of choice, I would say that I have choice functions, and then the well-ordering principle says that every set can be well-ordered. And the reason is, I will say in a few minutes, that these are not equivalent in ZFC. These are not equivalent with once you remove power set. And just to make it easier for me to put things on the slide, I'll let HC be the assertion that every set is countable. Okay, so it's a folklore theorem that the following theories are bi-interpretable. Second order arithmetic with the choice scheme, and Z of C minus plus the assertion that every set is countable. And I can sketch the argument. It isn't very difficult. So given a model of Z2 together with the choice scheme, the way that you build sets out of it is you build sets out of extensional, well-founded relations that you have available in the model. So as I said, last time, the model thinks that a lot of the subsets of natural numbers that it has are relations. Some of them it thinks are well-founded, and some of them it will think are extension. We will take all of those, and we will think of them as coding transitive sets. This is an obvious thing to do, and once you do that, you can define a membership relation on the equivalence classes of these extensional well-founded relations, and you can do all of this definably inside the model, and then the structure that you get in this way, it's not difficult to verify, satisfies ZFC minus, plus of course every set is countable. So this is in one direction. In the other direction, if you have a model of ZFC minus plus every set is countable, its model of second order arithmetic has to satisfy Z2 plus the choice scheme. And if you do the construction again, so if you take this model of second order arithmetic and you look at what you can build inside it by looking at these extensional well-founded relations, you get your model of ZFC minus back, and hence the bi-interpretability. Okay, so in this sense, I can really think of models of second order arithmetic as, in a hidden ray, models of a relatively strong set theory, I would say. But okay, so ZFC minus is really nowhere near as nice as it looks compared to when you have power set available. Once you remove it, lots of things that you would like to be true fail to be true. Let me give you some examples. So as I already mentioned, once you remove power set, replacement and collection are not equivalent. This was an old theorem of Zarak that we expanded on. Also, Zarak showed that various formulations of the axiom of choice are not equivalent. So having choice function is not as strong as having well orderings. And there are open questions surrounding Zorn's lemma. I think it's not clear how it fits with these, but seems to be a very difficult question. Another thing that fails in ZFC minus is something that, so this was a result about models of ZFC that was shown to be true when I was a graduate student. So now about 20 years ago, I'm getting old. But back then it was extremely exciting, and this was this ground model definability theorem. And what it says is that the model V is always definable with a parameter in its forcing extensions. And in fact, you have a uniform definition that works in every forcing extension. And this theorem has had many applications in set theory, and has resulted in a lot of work. And the point here is that it does not hold in ZFC minus. So this extremely nice theorem that you would like fails. Another example of a failing ZFC result is the intermediate model theorem, which says that if you have a model between V and one of its forcing extensions, then it too has to be a forcing extension.
Vika, sorry, can I ask? So this definability of the ground doesn't hold, but how about the whole forcing machinery? Is not problematic with ZFC minus?
Not at all. No, forcing machinery works without any problems.
I see.
Class forcing is a little bit weird, but set forcing works perfectly. Yes, I should have said it. I mean, the forcing machinery, you can do, so models of ZFC minus arise everywhere in set theory, and people work with them all the time. And a lot of the machinery does work there perfectly. So I should have mentioned that. So thank you for that question.
What do you mean by saying class forcing is weird in the non-power set context?
I mean, it doesn't stuff fail. You sometimes cannot verify that certain things are pre-tame, which would otherwise be pre-tame.
I guess I don't know offhand, but you would know this better than I.
Like Edward 1 or something doesn't work the same, for instance, is what I was thinking of. Because it's not, it may not be distributive anymore, right?
Okay, I see. Yes.
Right?
Yeah, it can, because you need, this is your result, you need DC.
Yeah, that's what I was thinking.
Okay. But is this, I guess maybe it is specific to class forcing then.
Yeah, I think it is specific to class forcing. And I'll come back to whatever I just said to Cameron in a second.
May I ask, is that the Zarach of Wrocław and Stroudsburg fame?
I think there's only one.
Yes, yes, yes. I think in the whole world there is just one Zarach.
Yeah, so I think it is. And he writes wonderful papers, which are so difficult to read, which is very unfortunate, especially for people like me who want to generalize some of his results. Okay, so next thing that.
Sorry, Vika, I'm really sorry to interrupt, but
go ahead.
the thing that I'm like missing, I think, is like, what's Z2 again? Is that?
Z2 is full second order arithmetic. So what it means is that any collection, any subset of the model definable by a second order assertion is a set. So it gives you maximal definability. Anything that you can define using second order quantifiers is a set.
But it's like a model of piano arithmetic.
Much more than that.
Okay.
Because you want to talk about the second order part, right? The sets that it has. In piano arithmetic, only numbers are important, but here you have sets of numbers as well. And it has potentially much more complicated sets than a model of piano arithmetic would have, because there we only think of it as having first order definable sets. But here you can have second order definable sets. So
you can do a lot of analysis in Z2.
Yeah, which you couldn't do just in a model of PA, exactly.
You can say for all functions or something.
Yes, you can define things using the quantifier for all functions, exactly.
Okay, thank you.
So you can argue that if you use such a quantifier, then the function that will satisfy the definition actually exists. Okay, so there's an obvious corollary of the result that I just showed you for models of ZFC minus. So models of ZFC minus, you can ask for an analog of this dependent choice scheme. And this is what I call the DC scheme. The obvious analog in a model of ZFC minus of the dependent choice scheme says that every definable relation without terminal nodes has an infinite range. So DC, the usual DC, dependent choice, holds in any model of ZFC minus because it has a C. But this is saying that this is not a set relation. It's a definable relation, so it's a potentially stronger statement. And the obvious corollary of the result that we have is that the DC scheme can fail in a model of ZFC minus, and the model in which the model that we build in which it fails is the H omega 1 of this symmetric model N. Okay, so why do we care about the DC scheme? Well, let's look at another scheme that should be very familiar. This is the reflection scheme. The reflection scheme, and I should say, a DC scheme obviously holds in ZFC because you can reduce class relations to set relations, which you cannot do here. Okay, so let's look at the reflection scheme. The reflection scheme says that every formula with parameters is reflected by a transitive set. So given a formula phi x and a set A, we have a transitive set model. I should have put set on all of these. We have a transitive set model that has A as an element and reflects V with respect to this formula. So it's very easy to see that the reflection scheme again holds in ZFC because rank initial segments V alpha out of the von Neumann hierarchy, if you go high enough up, are going to reflect any phi x. So because of the von Neumann hierarchy, we have the reflection scheme, and in the absence of von Neumann hierarchy, we will not. And the reason is that over Z of C minus, the reflection scheme is equivalent to the DC scheme. And that's what makes, I think, both of them very, very interesting. And so if you have a failure of DC scheme, I also must have a failure of the reflection scheme as well. So what is the reflection scheme good for instance? And this is what I was sort of alluding in my answer to Cameron's question. So if you've done model theory with models of set theory, what you often need to do is, given a model of set theory, it may not have a definable global well ordering, for instance. So it doesn't satisfy global choice. But what you can do with any model of Z of C is that there always is a global well ordering that you can add as a relation on the model. And then Z of C is going to continue to hold in the language with the relation. And the way that you argue this is you force over the model to add this class, this global well-ordered class. You cannot do that over Z of C minus unless it has the reflection scheme. In fact, being able to do this is equivalent to the reflection scheme. So this is one potential use of the reflection scheme. Okay. Now, this is a question that I didn't know about, but I recently got an email from a proof theorist, Anton Freund, who I've never met before, and he asked a really great question. He said, let's define the weak reflection scheme as follows. So we eliminate the parameter in the reflection scheme. So what it says is if V satisfies phi, then there should be some transitive set model which also satisfies phi. This is extremely natural. And what he asked me was whether it held in this model that we constructed. And I think the answer is obviously no, because of is obviously yes, it holds because of Schoenfeld absoluteness. So let me sketch you this argument. Okay, so I want to argue, we have the symmetric model N, and I have its H omega 1 in which the reflection scheme fails because the DC scheme fails. But I claim that the weak one holds. So let's suppose that it satisfies phi, that this H omega 1 of N satisfies phi. Well, I started in this model of Z of C, which is the forcing extension L of G, and because it has choice, it can construct a countable transitive model M that satisfies phi. But such a countable transitive model N is coded by a real, and therefore its existence is a sigma 1 to assertion, which therefore has to be true in the symmetric model N as well. And therefore, using the strategy that we have used up to this point, you cannot hope to violate the weak reflection scheme. So if it fails, we need an entirely new strategy of constructing counter example. So this seems to be a very difficult question. It seems both difficult. I have no intuition for it. I don't know. I think it should hold, but I have no idea how to show it. And the other, I think, really super interesting question is, okay, as a set theorist, I am really not interested in models of Z of C minus in which every set is countable. I'm interested in models of C of C minus with lots of uncountable cardinals. In fact, maybe with inaccessible cardinals, etc. So I would like a failure of the reflection scheme in one of these large models. And this is what originally motivated the questions that I asked, because, so in the same way that Z2 plus the choice scheme is bi-interpretable with Z of C minus plus every set is countable, a version of Z of C minus with an inaccessible cardinal is bi-interpretable with Kelly-Morse. So if we can get an analogous result for Kelly-Morse, we would have a failure of reflection in these very large models of Z of C minus. And thanks to this talk, I again finally started working with Sai on this question, and we're very optimistic, but there are some obvious obstacles, and we'll see what comes out of it. Phew, okay, I'm done.
Thank you, Vika. Okay, time for clapping. And time for questions.
Ken?
Yeah. Just giving other people a chance to formulate their questions. Yeah, I remember going way back as and one of Cohen himself, Paul Cohen himself, posed a problem which he had to solve because no one else could apparently, whether to build a non-standard necessarily, build a model of ZFC with of ZF with an automorphism of order 2. Now,
Okay.
with that question, and it's a tricky argument, and some of your arguments here bring me back to the way that argument went. But is that question relevant to Z2? That kind of question?
I don't know. I mean, so building these kind of automorphisms sounds very much to me like building automorphisms of a model of PA, which is Roman, which is something that Roman is very good at, and Ali has done a lot of stuff with. I know very little about it, and I wouldn't know. I don't know.
See, because that was Cohen's original attempt at proving the independence of the axiom of choice, was to build such a model. Yeah,
it's really interesting, and that would work with non-standard models, which none of this has anything to do with. And does he end up doing it?
Pardon?
Is it written up?
Somewhere, yeah. Yeah, it's an obscure publication.
If you happen to find it, would you send me?
Yeah.
Because
sure,
I think this would be interesting in and of itself.
Yeah. Yeah, there were, yeah, the other question he posed was about the relationship between the height and the width of models. Can you build models which are countably high but have non-countable many, say, reals in them? He was interested in that kind of question too.
But I think, I mean, my guess is people like Ali have probably now a lot of techniques for building these kinds of automorphisms of non-standard models, because I remember looking at it, but I don't know, it would be really interesting to see and compare, I think.
Okay, I'll see what I can do.
All right, thank you. Thanks, Ken.
I had a question that you had a theorem which seemed really interesting that I wasn't aware of, but it seemed like there was an axiom that was equivalent to a notion of forcing. It was right at the end.
Oh yeah, so it's an axiom that's equivalent to a notion of forcing behaving in the way that you want it to behave.
Oh, okay, that's
which is really weird, but happens to be true in ZFC minus. And that notion of forcing happens to be very easy. It's add ORed 1. So what you're doing is you're adding a class to ORed. And this forcing notion only behaves well if you have DC scheme, and does not behave well otherwise.
Oh, thank you.
Can I ask a question about the same slide?
Yep.
So you formulated this as being about ZFC minus, but of course you could do a second order context with like Gödel-Bernays minus. Do you know how strong you can make the second order axioms in this context and still have this failure of the reflection schema? So if you did like Morse-Kelly minus, could reflection still fail?
Wait, let me see if I understand what you're asking.
Well, because so that context, the schema is just like a single second order assertion.
Okay, but so this is right. So these models are obviously models of GB minus, but
Right.
no, but look, my counter example is H omega 1 of a model of zeta.
Okay, so you're getting full Kelly-Morse plus
I
class
get
choice.
Km minus 3. In fact, I think K minus plus the choice scheme. I get a lot, right?
Okay.
So I think, yeah, if I understand what you're saying, then it's going to be very strong. It won't help you to have these. I mean, having the second order objects available won't help you because it just doesn't exist in this much huger model. There's nothing here about definability, just from the construction.
All right, great. Thank you.
Okay, no more questions? No more questions, so let's thank Vika again. And thank you, Vika. Excellent talk. Thank you very much. And we have one more MOPA talk scheduled next week. Do you know, Vika, what it's going to be about?
It's on the website. It's continuous model arithmetic, I think. So I have the.
Oh, I see.
I think I have the abstract up. It should be up.
Oh, I see. I didn't know that. Sorry about that. I should have known. Yeah.
Is
So
that
take a
Joel
look.
speaking?
Joe will speak, but it will be
Okay.
earlier. It will be earlier next Wednesday.
Yes, it will be 12 p.m.
12 p.m. All right.
12 p.m. Yes. 11 was Joel had some meetings, so we decided on 12.
Okay. So see you all next week then. Thank you.
Jim, Carl.
Thanks,
Thank you
Vika.
for the excellent talk, Vika.